Hi, students, and welcome to today's lesson. I'm Mrs. Baidani. Today, we will explore the question, why is the moon visible at different times of day? Are you ready? Grab your pencil and your science journal, and let's get started. Imagine you are looking out a window one evening, and you see the moon just above the horizon. You come back to the window hours later, and notice the moon is in a totally different place. The moon has moved. Now it's higher in the night sky. Early the next morning, you stretch and yawn and glance out the window. You don't see the moon at all. The moon must have set while you were asleep. What interactions between Earth and the moon cause the moon to rise and set? Well, we learned that the rotation of Earth causes the sun to appear to rise and set. And we've seen that the moon appears to move east to west, just like the sun does. Do you think Earth's rotation is also responsible for the moon's apparent motion? I think so. In our last lesson, we created a data table of moonrise and moonset times for Washington, D.C. in 2019. We analyzed the data from 7 days in January and realized that the moon rises and sets between 30 minutes and an hour later each day. We can call this pattern a staircase pattern because our data looks like a set of stairs. How could you explain the changing moonrise and moonset times each day? Well, if the moonrise and moonset times can change, then the moon must be changing positions relative to Earth, right? In fact, in our last lesson, we saw that the moon is sometimes visible during the day. So sometimes the moon is on the daytime side of Earth, and sometimes it is on the nighttime side of Earth. We know Earth is moving, but do you think the moon is moving as well? Let's gather more evidence to help us answer the question, why is the moon visible at different times of day? To help us answer our question, let's look at moonrise and moonset times from the whole month of January. What trends do you notice in the moonrise and moonset times throughout the remainder of January? I notice that the moonrise and moonset times continue to be later each day. Wow! And hey, the moonrise times are the same on January 1st and January 30th. The moonrise on January 1st was around 3 a.m. That moonrise time repeats on January 30th, which is 29 days later. Do you notice that too? What else do you notice? Let's look more closely. Wow, look at this data. The length of time that the moon is visible gets longer during the middle of the month and shorter again at the end of the month. How can we determine if there is a long-term pattern in the moon's visibility? I think we need to see more data, don't you? We need data that covers more than 1 month. So let's look at data tables of moonrise and moonset for February and March. What trends do you notice when you compare the January, February, and March datasets? I think we should look at these datasets one at a time, don't you? We've already looked at January, so let's look more closely at February. Hey, look at the moonrise time on February 28th. What do you notice? Do you see that the moon rises around 3 a.m. on February 28th? So the moon rose at 3 a.m. on January 1st, January 30th, and February 28th. Each of those dates is 29 days apart. Will the pattern continue in March? See if you can find a 3 a.m. moonrise in the March dataset. Did you find it? On March 30th, the moon rises at 3 a.m. March 30th is 30 days after February 28th, the date of the last 3 a.m. moonrise. So the cycle seems to repeat every 29 to 30 days. In fact, the moon's monthly pattern repeats every 29.5 days. The pattern takes about a month to complete, which is why the word month comes from the word moon. How could we predict what the moonrise time would be 30 days from now? Well, we just learned that the moon takes about 30 days to repeat the pattern, right? So the moonrise time 30 days from now would be about the same as the moonrise time today. Remember our virtual students, Janila and Shanila? A few lessons ago, we added the moon to our EarthView student model. Let's apply what we've learned today to our model. How can we modify our model based on the moonrise and moonset data? Maybe the student representing the moon can move based on the moonrise times. We know the moon rises over the eastern horizon, and that the moonrise happens about an hour later each day. So every time the Earth student completes one rotation, the moon student should move so that the Earth student sees the moon pass by her left hand an hour later on the 24-hour clock. Which direction would the moon student need to move so that the moonrise happens later each day? Well, if 12 a.m. or midnight is here, and 12 p.m. or noon is here, then the moon student needs to move in a counterclockwise direction, right? That's right. The moon orbits Earth in the same direction of Earth's rotation, counterclockwise. Your first task after this lesson will be to answer a question about the moon's position in the model. And remember how we noticed that the moon takes about a month to complete the pattern and for moonrise to return to the same time? Why do you think that is? Well, the moon takes about a month to complete one full orbit of Earth. The moon starts in one position relative to Earth and returns to that same position about 30 days later. That's why moonrise occurs at the same time about every 30 days. Your second task after this lesson will be to answer a question about the moon's orbit. So let's look at our 24-hour clock model with our virtual students. Our Earth student is in the center. On March 1st, the moonrise time was 3:30 a.m. That means at 3:30 a.m., the moon student should come into view over the eastern horizon. Let's use a three-dimensional model to show the position of Earth. The moon comes into view as the left side of the Earth model's face turns to face the moon. The left side is the eastern horizon. The moonrise on March 2nd is about 1 hour later at 4:30 a.m. Which way does our model need to turn? What do you predict? Let's see if your prediction is correct. If you said Earth needs to rotate counterclockwise so that the moon comes into view at 4:30 a.m. over the eastern horizon, you got it. Okay, here's a challenge question for you. Let's predict it's March 15th. The moonrise is at 12 p.m. or noon. Shout out how we should position the three-dimensional model to represent Earth. Did you say the model should be facing 12 p.m. so that she can see the moon student out of the corner of her left eye? That's where the eastern horizon would be, right? Great job. So are we ready to answer our question, why is the moon visible at different times of day? I think we are. We learned that as Earth rotates, the moon is also orbiting Earth. Because both are moving, the moon can be visible during both daytime and nighttime. The moon takes about a month to complete a full orbit around Earth. So the moon appears at different times of the day as its location changes around Earth. Great work! Your final task after this lesson will be to summarize what you've learned about the moon. But I still have some questions. Do you? Look at our second driving question board category. We've answered a lot of our questions about the moon, but I don't think we have answers to these questions yet. Why does the moon's shape change? Does the shape of the moon change during a month like moonrise and moonset times do? Does the moon look the same from the opposite side of Earth? We've learned so much about moonrise and moonset and how movements of the moon and Earth interact. But I can't wait to explore our remaining questions as we continue to learn about the moon. Let's review your tasks for today. First, answer the question about the moon's position in the model. Second, answer the question about the moon's orbit based on the model. Third, summarize what you learned about the moon.